Okay guys, in this video we're going to talk about the inverse of square metric. So what we have learned before, the minor, the cofactor, the determinant and so on are going to be used here. So as you can see here, in the topic of inverse of square metric, we are going to learn on the basic idea of inverse, and then we're going to look for inverse 2 by 2. Looking for inverse 2 by 2 is quite easy because we have a formula. We just plug in and calculate, and the real thing comes when we want to find inverse for 3 by 3 or higher. So to do that, right, we are able to use cofactor method, which is by using the method of cofactor and adjoints that we have learned before, right? Finding cofactor, finding adjoint, and lastly we're able to get the inverse of that metric. Or we can also use the other one, which is called ERO. This is actually new, elementary row operation. We still haven't learned about it, so we are going to do it later. Even so, the determinant is actually being used here in the formula of 2 by 2, which is this. Look at the denominator here, you have the determinant. Okay, so let's talk about it now. If A is a square metric of order n, and if there exists a metric inverse such that this, so A, the original metric, times with the inverse metric, right? Or the inverse metric times with the original metric, you should get the identity metric. Remember, identity metric, which is in this form, right? 1 and 0. So then if they are in this form, then the metric inverse A is called the multiplicative inverse of A, or more simply the inverse of A. So if they fulfill this requirement, and this can be called an inverse of that original metric. Okay, so let's see example. Show that B is the inverse of A, where this is A, metric A, and this is metric B. So to show that, right, by applying what being told in definition 2.2, we just prove it by multiplying A with B, and we should get the identity metric. And we go the other way around, B and A, we should also get the identity metric. So when we do it like this and we get the n identity metric, we can say that hence A times B equal to B times A equal to identity. So B is the inverse of A. Okay, or in other words, B here is this A inverse. Okay, the metric B here is actually the A inverse. Okay, that is how to prove it. Okay, you can try to do it to do this exercise. Try to prove it whether B is the inverse of A or not. And on the side note, right, just to know whether that particular metric has an inverse or not, because not all square matrices has inverses, right? If you calculate for the determinant and you get 0, right, when you do cross multiply, and right, like we did before, we get 0, and it indicates that that metric does not have an inverse. But otherwise, it means that it has an inverse. So let's look at the formula in finding inverse of a 2 by 2 metric. So this is the metric A, B, C, and D. Then the A inverse is this, 1 over the determinant of A multiplied with, alright, this metric is actually A and D being changed their place, and B and C being changed their symbol to negative. So this formula actually was retrieved based on this these properties, but we are not going to discuss that because we're going to take another video. So let's just apply it. Be familiar with the formula, and this is only applicable for 2 by 2. And let's look at it first. The metric A is invertible, meaning that can be inverse if and only if AD minus BC not equal to 0. What is AD minus BC here? AD minus BC here is actually this, or in other words, the determinant, right? The same as what we discussed before. If the determinant of A not equal to 0, it means that it does have an inverse. But if it is equal to 0, does not have an inverse. In other words, it's not invertible, right? Logically, just by looking at this formula, 1 over any value other than 0 can be calculated. But if you calculate determinant and you get 0, 1 over 0, you will get math error in your calculator. So if the determinant, which is this formula, equal to 0, then A does not have a multiplication inverse, or don't have inverse. Okay, so let's look at this example. Find the A inverse if it is this. Given A is this. First, let's try to directly calculate the determinant. -1 times 4, -4, minus with 3 times 2, which is 6, right? So -4 plus 6. So -4 plus 6 is 2, which is not equal to 0, meaning it indicates that it does have an inverse. So we can proceed with the formula, right? This formula. So we just simply, for this one, we don't need to really calculate it again. We know that we already calculated it here. So we just simply input 2, because it is the formula of determinant 2, and we input everything here. So we have D, -C, and -B, -C, and A. So just input everything. Okay. So for D, we put input 4. For -B, we have B here -2, so with negative it becomes positive. And for C, negative, we input it as -C, which is -3. And for at this area here, it is A, which is -1, so -1. So just simply multiply it using the idea of scalar multiplication. 1 over 2 times 4, 1 over 2 times 2, 1 over 2 times -3, and 1 over 2 times -1. So there you have it, the inverse of A. Okay, this is for 2 by 2. So for this exercise, let's see. Let's just get the idea whether they have an inverse or not. So 3 times 2 is 6. 6 minus -2. So 6 plus 2 is 8. Yeah, for A, it actually have determinant is not equal to 0. So we can find the inverse. Try to find the inverse. As for B, 3 times 12. 3 times 12 is 36. 36 minus with 36, 0. So meaning for B here, it doesn't have an inverse. So that is how you find inverse for 2 by 2. In the next video, we're going to talk about finding an inverse for 3 by 3 or higher using cofactor method. Right? By saying cofactor method, it literally means that we're going to find a minor, we're going to find a cofactor, and later we're going to find an adjoint before we multiply with 1 over determinant. Okay, as simple as that. Okay, and the next will be finding inverse using elementary row operation, or ERO. Okay, so thank you.